So now I want to move into the actual experiments and how we put our protocol to the test. And to do this, we started with actually trying to replicate the basic exposed node scenario. Um, and this was done in an iterative fashion where we determined the network and physical limitations of our model. And so we had a general location model where we could specify coordinates of various nodes, and there was no direct mapping between these coordinates and actual location units. And so we had to find the various ranges of our receivers given our network parameters, and then generate traffic that would saturate these links so that we could get verifiable exposed node instances. And what we essentially found was that if we place nodes 0 and 1 at the coordinates 0 and 200, and nodes 2 and 3 at 800 and 1000, that we could replicate the exposed node scenario. And these coordinates you can think of as a one-dimensional node structure, where nodes 1 and 2 are within range of each other, but nodes 2 and 0 are out of range, and nodes 1 and 3 are out of range. So if we think back to the original picture that we saw for the exposed node instance, this replicates that same scenario. And so to actually saturate the link, we had nodes 1 and 2 be the senders in this topology, and they generated UDP packets with 2048 bytes of data sending at an interval of 0.003 seconds, and we ran our experiment for a duration of 5 seconds. And naturally, nodes 0 and 3 are the servers accepting all this generated traffic. And so this brings us to our actual observed traffic for this experiment. And this is specifically the observed traffic at node 1. And if you refer back to the previous slide, node 1 is the far left sender. So it is an instance of the exposed node problem. And what we observed is that for the original protocol, node 1 was able to achieve roughly half of the total offered throughput. I would say it's more than half. It is about 3 megabits per second out of a total offered 5.5 megabits per second. But essentially what is happening is that nodes 1 and 2, as in the two senders in this topology, are essentially sharing the channel because they are both trying to offer traffic the entire time to totally saturate the link. And we are essentially receiving half of the maximum channel bandwidth at each node. One final thing to note on this slide is the star beside the throughput for each of these nodes. And this is due to the great questions that were asked during the mid-semester presentation. And we will clarify this in a couple slides, but there were some minor issues with our calculations of this throughput, which were largely a function of our understanding of NS3 and how they were performing their calculations. But we will get into the details of this later. And so this brings us to a Wireshark graphic of the received packets verifying that all of the results seen in the previous slide were actually received from the node at node 0. Similarly, this is the received packets at node 3. The packets were received from node 2, and the graphic here is once again graphing the packets per 100 milliseconds as a function of time. And if you perform the calculations, you should get the throughput shown at the slide 2 slides ago. And so now we want to demonstrate how our protocol modifications perform against the unmodified protocol. As you can see, the packets per 100 milliseconds increased from right around 20 packets per 100 milliseconds to around 35. And this is reflected in the fact that our throughput achieved was right around the throughput offered. Once again, there's a star besides this throughput, and this is once again a function of the questions asked in the mid-semester presentation, which we will get to shortly. But at a high-level overview, in this basic form, our protocol seems to perform extraordinarily well compared to the original. We are able to almost double the throughput achieved. And this is largely a function of, just our intuition in that the channel is actually free to transmit across, and that the attenuation from the interfering signal will not be perceived by the receiver. And so, as I mentioned previously, this brings us to a clarifying question. And this is essentially, how is our TX offered being calculated along with the throughput? And the answer to this is in the built-in structures in NS3, which are known as flow monitors. And a flow monitor is essentially a way of tracking all of the packets transmitted from a single source to a single destination with the same protocol. So since we were generating UDP traffic with these 2048 bytes, these numbers correspond to, UDP packets sent from a given sender and received at a given receiver. So if something gets queued and never sent, then that packet will be incorporated into the TX offered calculation, but not the throughput calculation. And you can see in an example calculation, this isn't exactly the number that we reported previously, but this is because the TX offered calculation includes header bits from layers 1, 2, 3, and 4, whereas the bytes that we were specifying in our UDP packets were strictly for the UDP packet size and not the actual headers. So expanding on the base case, we wanted to look at how our performance varied with, or as distance changed between the inner nodes. So if we fix nodes 0 and 3 and vary the position of nodes 1 and 2, how does our performance change as essentially the instance of the exposed node problem becomes more severe? Specifically, this translated into iteratively moving the central nodes 100 units closer, and then observing the achieved throughput given the same traffic patterns. And this brings us to some of the results for this experiment. And what this graphic shows is a measure of throughput in relation to the difference in central node position. And looking at this graph, you can see that the red and blue lines represent the modified protocol performance, whereas green and yellow are for the original protocol. And looking at some key areas in this graph, if we start with small differences in central node positions, this means that the senders are closer together or the instance of the exposed node problem is more severe. And you can see that in this case, our modified protocol is performing slightly worse than the original, or at least comparable. And if we look at this region between 300 and 500 units, you can see that we are straddling the original senders. And this indicates that we are unfairly sharing the channel capacity. However, as this distance increases, our modified protocol vastly outperforms the original protocol. We are essentially able to double the total offered throughput of our senders. And so you can begin to see this region where you can put in limits of our implementation and achieve overall increased network performance. So after seeing how we performed in relation to the base case, we wanted to then expand on this base case in a way that we deemed the iterative base case expansion. And this involved, kind of the similar approach of varying the two inner node positions in relation to each other, and then moving the receiving nodes further away from each other, and then repeating the same experiment. And essentially this is the same as just observing how performance varies with inner node position as well as outer node position. And this manifested itself in the form of moving the central nodes consecutively 100 units closer, and then pushing the outer receivers 100 units apart, which again corresponds to 50 units each. Once again, we are maintaining the same traffic patterns as before, so we are trying to fully utilize the network bandwidth in terms of each sender-receiver pair. And this brings us to the results for the iterative base case expansion experiment. And so what these graphs are demonstrating are the observed throughputs as a function of the relative distance between sender and receiver pairs. And so as these sender and receiver pairs get closer together, which corresponds to lower x-axis values, the corresponding distance between the two senders is increasing. So looking specifically at the graph to the left, which is only focused on the modified results, we can see that with a low distance between sender and receiver pairs, we are achieving close to the maximum offered throughput, between our senders. And there's a lot going on in these graphs, but you can see that as this distance increases between sender and receiver pairs, which corresponds to a decreased distance between the two senders, we drop in throughput. So our protocol is unable to achieve this maximum throughput throughout the duration of this experiment. In terms of the original nodes, they are only able to achieve a maximum of, right at half of the maximum network bandwidth. And so there is that region up until right around 400 distance units between sender and receiver pairs, where our protocol modifications are vastly outperforming the original protocol. But then if you look at the rightmost portion of both of these graphs, so if the distance between senders and receivers is maximum, the original protocol is able to perform in a more fair notion of throughput. So you can see on the left that for our modified senders, they achieve between right around 2.9 and 1.9 megabits per second for their throughput. Whereas for the original protocol, the nodes are achieving from right around 2.9 to around 2.45 megabits per second. And so on average, we are performing about the same as the original protocol. But in this kind of extreme sense of these graphs, our protocol modifications are performing less fairly in that different nodes achieve a greater difference in throughput. But there is that region where our protocol modifications vastly outperform the original. And this brings us to a graph of the average throughput for our modified protocol implementation compared to the original protocol in terms of the relative distance between client and server. And these values were averaged over the client-to-client distances, and it is a representation of the performance that we can expect at a given distance between client and server. So as this distance is minimized, as in the X values are lower, we can achieve a much higher throughput than what the original protocol could achieve. We almost double that average throughput. That being said, as the relative distance between client and server expands, or the distance between the two clients contracts, our throughput ends up dropping. And this is largely a function, again, of kind of that noise threshold where our receiver isn't able to respond to our transmitted packets in a perceptible way. This comes back to the whole issue where an instance of the exposed node problem ends up being, a pseudo instance of the hidden node problem, where even though we're sending UDP packets at the data link layer, we are still, acknowledging the packets that we received on the server. And so as the clients move closer together, the overall noise or interference that gets perceived at that client increases. And so we are unable to hear our server responding to our sent packets. And so our throughput ends up dropping, due to these missed acts. But this graphic really highlights, the threshold at which we are able to outperform the base protocol.